my name is Mark Donegan. I'm an applications engineer in the Linear Product Group in Analog Devices. I'm here to talk about a high-performance DC and AC contactless current sensing solution using ADI's newest magnetic sensor, the ADAF1080. I will introduce the product as well as examples of contactless current sensing solutions. The first example is a single ADAF1080 magnetic field evaluation board. The other solutions focus on contactless current sensing using an array-based sensor configuration, which has advantages over existing solutions such as Hall effect, shunt-based, or current transformer solutions. Before we begin, let's review some basics. We know that a current-carrying wire generates a magnetic field. Using Ampere's right-hand rule, we can also predict the direction of the magnetic field. The field strength at a radius r is proportional to the current carried, and can be seen in the formula with B representing the field strength and or the radius from the center of the wire. A magnetic field sensor at a known position can measure the magnetic field, and then you can calculate the current in the wire in a contactless fashion. The ADAF1080 sensor produces an output voltage proportional to the magnetic field strength. The output voltage is equal to the sensor's sensitivity multiplied by the detected magnetic field along its sensitivity axis. The ADAF1080 sensor is an 8 millitesla field sensor. It integrates an anisotropic magnetoresistance or AMR sensor along with the necessary low noise circuit conditioning for ease of use. It features a gain programmable chopping amplifier, temperature compensated sensor bridge, and magnetic flipping for sensor offset removal. The chopping amplifier corrects for both initial offset, typically in the order of microvolts, and offset drift over temperature. The ADAF1080 is capable of both AC and DC measurement, unlike current transformers or Rogowski coils. It's a coreless design, resulting in negligible hysteresis compared to solutions that use the flux concentrators. It has a 2 MHz bandwidth, and finally, the low noise and wide dynamic range enables field measurements from nanoteslas to milliteslas. In terms of current, this translates to milliamps to thousands of amps. The ADAF1080 evaluation board comprises of a single sensor with ADI's system development platform for signal acquisition. In the demonstration, the board is placed inside a Helmholtz coil. The coil generates a very uniform magnetic field. Sweeping the field from plus 2 millitesla to minus 2 millitesla within this coil, we can observe the ADAF1080 output in the evaluation software. The ADAF1080 has a typical linearity error of 0.3% in this range. The field generated by a Helmholtz coil is uniform and well controlled. In current measurement applications, stray field and positional uncertainty play a role in the system accuracy. Stray field and positional uncertainty can be improved with this 3 or 6 sensor board. This 200 amp evaluation board is intended for the measurement of a fixed wire. It's a single analog output, and as with the sensor, it's also a coreless solution, meaning the hysteresis benefits of the ADAF1080 are maintained. The solution is capable of both DC and AC measurement, with a nominal range plus minus 200 amps, 0.25% linearity error, and overcurrent measurements up to 640 amps are also possible. Another example is this 500 amp current meter with LCD and digital output. This system consists of 16 sensors with a jaw opening to allow various wire gauges. It's a much thinner solution compared to existing handheld plant meters, which use flux concentrators or Rogowski coils. This system contains a sensor array, summing circuit, ADC, and a microcontroller with firmware to convert the summed sensor outputs to a current value. This solution also has a USB connection that connects to a software interface. In this setup here, we are measuring zero current, and we can see that the noise is less than 1 milliamp RMS with a 4 Hz update rate. At 10 amp DC current, the plot shows approximately 0.7 milliamps RMS of noise. This means the system has about 120 dB dynamic range. The linearity error of this system is typically less than 0.5% after a single point calibration and the onboard correction algorithm. Common issues with existing handheld meters include hysteresis and the need for continual offset nulling of the system due to saturation of the cores and this hysteresis. As with all the solutions here today, there is no core required and hysteresis is negligible. This type of solution also eases the manufacturing burden without the use of these core materials. Here's an example of an AC measurement, 10 amps at 100 Hz flowing through the cable. Again, noise performance is less than 1 milliamp. The existing solution has a frequency range up to 1 kHz, and this is easily extended with alternative filtering designs and sampling rates. These differentiated solutions are all enabled by AMR's higher dynamic range, higher bandwidth, and thinner form factor over existing technologies. All of these demos are actively sampling, with the ADAF 1080 expected to release in May of 2021. AMR offers game-changing performance to any application using contactless current sensing. Contact an ADI sales representative to order an evaluation board today to see how AMR can improve the dynamic range and offset of your system.